Okay, ladies and gentlemen, we are going to try to take a look at the second free response question, and I got to say, this is one of my favorite kinds of free response questions. Just looking at the picture here, we've got a table. There's a block resting on the table. There's another block here on a string. It's probably going to swing down, hit this block, and the second block is going to fly off the table and land on the ground over here, and the first block is going to swing up some lesser distance. This is the kind of thing that the AP test writers just love, multiple steps in a problem, multiple parts of the curriculum. Although this one really focuses on the early mechanics we did, which is kind of good because they're gonna do that on your test. Your test is going to be a take it at home test. It's going to be 45 minutes long, and it's going to focus on the earlier parts of the curriculum. So, assuming everybody goes in the same order that we do, that means that the simple harmonic motion and maybe some of the rotation is just not going to make it. But let's go ahead and read the question and have a look at what's important here. First of all, I'm noticing on the drawing that the mass of block 1 is 3 times m, and the mass of block 2 is 1 times m. So I'm going to use a lowercase m when I'm just writing down the equations, but then I'm going to use a capital M when I start putting in the actual values for this problem. Okay, a pendulum of length L consists of a block 1 of mass 3m attached to the end of a string. Block 1 is released from rest with the string horizontal as shown above. At the bottom of its swing, block 1 collides with block 2 of mass m, which is initially at rest, that's important, at the edge of a table of height 2L, that's important. Block 1 never touches the table. As a result of the collision, Block 2 is launched horizontally from the table, landing on the floor distance 4L away from the base of the table. After the collision, Block 1 continues forward and swings up. At its highest point, the string makes an angle theta max to the vertical. Air resistance and friction are negligible. Express all algebraic answers in terms of M, L, and physical constants. Okay, that's going to be important. Alrighty, so now we've read the problem. Let's see what kind of questions they're going to ask. And part A, determine the speed of block 1 at the bottom of its swing just before it makes contact with block 2. Okay, excellent. I don't think there's a need to draw the picture again, but maybe just because we're here doing this, let's draw the picture here. L, a mass of 3 times capital M, and then it's going to swing down here and be moving. That's L, and this is still 3m. So clearly we have potential energy being turned into kinetic energy, and that's a really simple problem to solve. So let's go ahead and do it. The potential energy in this case is m times g times h, again lowercase m because it's just the equation I'm using, and the kinetic energy is 1/2 mv squared. And it turns out the mass is not going to bite us at all because we're just going to move the 2 to the other side, take a square root, and wind up with the velocity at the bottom there is going to be root 2 GH. This is a result that we've gotten a number of times, but this is not the final answer to this question because they said it has to be in terms of M, L, and physical constants. So we have to replace the H with L. So V is going to be root 2GL. And then I'll just circle this so that they can find my answer and give me full credit. This is part A. Alrighty, good start. Part B comes in and asks us on the dot below, which represents block 1, draw and label the forces, not components, that act on block 1 just before it makes contact with block 2. Each force must be represented by a distinct arrow starting on and pointing away from the dot. Forces with greater magnitude should be represented by longer vectors. Okay, so they want a free body diagram, but they don't want a slapdash free body diagram. They want the whole Megillah. They want you to be very clear about what you're doing. I don't know why I always grab the red pen when we move to forces, but I do. So at the bottom here, when it's before it hits the other block, it's in this vertical position. So if we draw a dot for the block, there's clearly going to be some tension pulling upwards, and I'm going to abbreviate that with a T. And there's going to be some weight that the block has downwards. I'm going to abbreviate that with M times G. Now you'll notice that I made the tension force larger than the weight force. And the reason for that is that this thing is swinging in the arc of a circle, which means that there needs to be some sort of centripetal force towards the center. So the tension force has to cancel out the mass, or the weight, excuse me, and have some additional force to go on. So the scoring on this was 3 points, one for each of these two forces, and no more than 1 point total if you put extraneous forces on there. The third point, one for each of the forces, the third point was for having the tension force be longer than the weight force. Okay, moving on, we're going to look at what they ask. So far, they're leading us through this very slowly. C. Derive an expression for the tension in the string when the string is vertical, just before block 1 makes contact with block 2. If you need to draw anything other than what you've shown in part B to assist in your solution, use the space below. Do not add anything to the figure in part B. Okay, so I think we can just look at this picture and go ahead and do C. C is going to be pretty straightforward. Because it hasn't hit block 2 yet, we know that the centripetal force is being provided by the tension minus the weight. And we're solving for Ft, the tension. Okay, so they called the tension Ft. I'll switch to that notation now. So if we want to isolate this, we need to bring this to the other side, and we need to say that the tension force is going to be the weight plus the centripetal force. Now the recipe for centripetal force is mv squared over r. And here's where we start plugging things in. Okay, we're going to plug in stuff. These are lowercase m's. We're going to plug in the real m's here. Ft is going to be 3 capital M times g plus 3 capital M times this velocity above squared. So we just get rid of the square root. So that's 2gl. And the radius of the circle is L. Okay, so there's some cancellation that goes on here. The L here and the L here cancel out. 2 times 3 is 6, so we wind up with 3 capital Mg plus 6 capital Mg, and the L's have canceled out, and that means that we have a grand total. Hey, look at this. I went below the fold. We have a grand total of 9 capital M times G. And now you can see why penmanship is so important here. This 9 and that G could easily look alike if you weren't too careful. So do be careful to make sure the grader can tell what you're trying to do here. I'm going to move my camera up a little bit here. I didn't get this quite right. I want to show the whole page when it's appropriate. Okay, moving down. Beautiful. Okay. Geez, now we're on to part D. That was pretty simple. Part D is below a little thing. It says for parts D through G, the value for the length of the pendulum is 75 centimeters. Okay, so maybe we're going to put some numbers in here at this point. The first thing they ask is to calculate the time between the instant block 2 leaves the table and the instant it first contacts the floor. All right, so if we look at the picture, we know that block 2 is going to become a projectile, and it's going to be a horizontally launched projectile. So it's going to fall to the floor with no initial vertical velocity. So regardless of how fast it gets projected off the table, it's going to take the same amount of time to hit the floor. And so let me recreate the drawing here for part D. We have a table and we have the floor. This distance here is 2L, and this block is going to be projected horizontally. It's going to land on the ground a distance 4L away. Now I'm going to refer to this diagram for the rest of this section here. So we need to find the time it's going to spend in the air. Well, the time it's going to spend in the air has everything to do with the height, and I'm going to use the Y Swiss Army equation. Y equals 1/2 acceleration times time squared. All right, I've left off the initial velocity term because, as I mentioned before, it's projected horizontally. I don't know if you want to maybe add some words to mention that, but I think as long as you get the right answer, they're going to be just fine with this. So that means that 2L is going to equal G over 2 times T squared. Now we're looking for the time, so we need to get this to the other side. That means that the time is going to be the square root of 4L over G. That's how long it's going to take to hit the floor. And since we know it lands a distance 4L away, then we're going to be able to figure out how fast that block was going. Well, let's see if that's what part E is. Part E, calculate the speed of block 2 as it leaves the table. Now, when I initially saw this problem, I thought, we're going to do a collision here, like a perfectly elastic collision or something like that. But no, what we have is we're going to figure out how fast block 1 was going before it hit block 2. We're going to figure out how fast block 2 is going after the collision from where it lands on the floor, and then we're going to do other stuff. to figure this out. So we need the speed of block 2 as it leaves the table. Okay, so now block 2, that happens in the x direction. So we're going to say that x equals velocity in the x direction times time. There's no acceleration in the x direction. And so the x distance it goes is 4 times L, and that's going to equal Vx times this square root of 4L over G. So looks like we need to do some magic math here on this thing. Oh, wait a second. You know what? I didn't finish part D because we have a numerical value now. All right, well, let me finish this and I'll leave some space over here for that. That means that what are we going to do here? We're going to say that Vx equals, and that'll be 4L times the square root of G over 4L. Let's see, 4L can come in as 4L squared on the top, and there's 4L not squared on the bottom, so we're going to wind up with square root of 4 GL. Okay, let me go back before we do this, and let's get some numbers in here, because t is going to be the square root of 4 times 0.75 over 10. You see, I'm going to use 0.75 as the L, and I'm going to use 10 for the V, and that's going to turn out to be 0.55 seconds. That's what should be circled, not that. This is true, but that's the actual answer. And then when we do this one, we're going to have 4 times 10 times 0.75 all under a square root. And near as I can tell, that Vx turns out to be 5.45 meters per second. There we go. Now we're getting numerical answers as they wished us to do. Wow, we're just powering through this. We got an F and a G to go. F says calculate the speed of block 1 after it collides with block 2. Okay, this is where you could run into a little bit of trouble if you don't remember what we said about collisions. Collisions that are elastic conserve both momentum and energy. Collisions that are inelastic conserve just momentum, but not necessarily energy. So we can't use energy conservation to solve this problem because we're not sure whether this collision is elastic or not. So let's go ahead and use momentum conservation. I'm kind of crowding this paper, but I'm trying to see if I can get this all done on one sheet. So let's figure this out. The momentum total ahead of time equals the momentum total afterwards. The momentum total ahead of time is the mass of 1 times the velocity of 1. Afterwards, we have the mass of 1 times the velocity of 1 afterwards plus the mass of 2 times the velocity of 2 afterwards. And now we're going to put in some real numbers here. So we have 3 capital M times this velocity of root 2 GL equals 3 capital M times the velocity of 1 afterwards, which is the thing we're looking for, plus just M times 5.45. Okay, my blue pen is kind of spreading ink everywhere. Looks like a couple things go on here. There's some cancellation, and I need to figure out what root 2 GL is in numbers. But all these masses are going to cancel out here. And so we don't really care about the mass, but the 3 is really important. Okay, so this is going to be 3 times, and let me figure out what root 2 GL happens to be in the real world here. So we have 2 times 10 times 0.75, and now that's 15. We take a square root of that answer, and we wind up with 3.87. So 3 times 3.87 equals 3 times the thing I'm looking for, plus 5.45. Okay, looking good. Looks like I need to do 3 times this 3.87 times 3 equals. I now need to divide by 5. No, I'm going to subtract 5.45. And then I need to divide by 3. And that's going to give me a V1 prime of 2.05 meters per second. All right, not too bad. Not too bad. Question is, can I squeeze in part G here at the bottom? I'm not sure. Yeah, we can do it. We can do it. Okay. No, it is not worth doing. So I'm going to get a new piece of paper here. So the last question says, calculate the angle theta max. Oh, I guess we knew that was coming. Calculate the angle theta max that the string makes with the vertical, as shown in the original figure, when block 1 is at its highest position. Okay, so now that we know that after the collision, block 1 has this speed of v1 prime, it is then going to swing up to some angle theta and stop. And this is just like the opening salvo of the problem. This is a conservation of energy problem. So the kinetic energy that the thing has turns into potential energy, and it will stop at its highest point. So the kinetic energy is 1 half mv squared. The potential energy is mgh. The m's cancel, so we don't need to worry that it's a mass of 3m. So we have v1 prime squared equals 2g. Now h. H is interesting. The height. Remember we did this thing when we talked about the pendulum, and we said that the height here is really a function of the length, and that h was equal to L times 1 minus cosine of theta. And you remember me telling you that if you just memorize this, you'll have the key to pendulum problems. So we are going to do that here. We're going to replace h with L times the quantity 1 minus cosine of theta. And then theta is what we're looking for. So let's just tell you what we're going to do. Let's do a little algebra here. So we're going to have v1 prime squared over 2gl is going to equal 1 minus cosine of theta. Theta comes to this side, this comes to the other side, and we'll realize that cosine of theta is going to be 1 minus v1 prime squared over 2gl. Okay, let's find this thing, and then we'll just take an inverse cosine. Okay, so cosine of theta equals 1 minus, and we just figured out this velocity. It's 2.05 squared over 2 times 10 times 0.75. And I'm going to calculator this thing into the next dimension. Clear, clear, clear. Okay, 2.05 squared equals, okay, divided by 2, divided by 10, and divided by 0.75. Forgive me for my non-algebraic way of punching things in, but I grew up with a much simpler calculator. Okay, and then 1 minus that answer gives me an answer of 0.7198. Okay, yeah, well, let's call it 0.72. Okay, that's good because the argument of cosine, or cosine itself, produces an answer that's between -1 and 1. So this is in that range. So let's take an inverse cosine of both sides and see what happens. So inverse cosine of that answer. And that means that theta is going to be 44 degrees, 43.9, but I'm rounding up. And so that's going to be my answer for this. So pretty good problem, pretty straightforward stuff. We have 2 pages of scribble scratches. The only thing I want to say was a little problematic is making sure you don't try to use energy here. Another thing that was problematic for me was remembering that after they give me numbers for the problems, I need to put those numbers in to get numerical answers. Another issue that you might have had is not realizing that these two forces are not the same, that when something is swinging in circular motion, that there needs to be additional force towards the center. The forces are not balanced. Other than that, this is a pretty straightforward problem. Now, let's talk for a second about the previous problem we did. I had a little mental vapor lock at the end of it, and then it came to me later what was going on. Ooh, I did not save. Okay, I didn't save the paper. Hold on a sec. Let me hang on just a moment here. Okay, I found my papers. I'm saving all my online lecture papers, for the Harmon Presidential Library. I had a brain fart when we did this problem, and I got to the end and I said, well, you could figure out that the force was equal to the weight when it reaches terminal velocity, or you could plug into this equation, just plug in t going to infinity. And if you did that, I freaked out because you don't get the weight. You actually get force going to 0. And that's why I vapor locked. But then I realized, hold on a second, this is actually the net force. And of course, when you're in a terminal velocity situation, then the net force is zero, because these two, the upwards drag force and the downwards weight, they're equal to each other. So I shouldn't have freaked out. I should have known that there was some good physics going on there. And so there you go. My faith in physics is restored, and now you know what was happening there. All right, folks, I'm going to try to get this posted pretty soon, and I'll get that last problem solved and out to you by Monday morning.